Okay, great. So, hi everyone. Today I'm going to be talking about message passing in machine learning, and this is a presentation based on the recent tutorial given by Professor Wissam Lee at NUS at Europe's 2021. And as usual, just feel free to interrupt at any point to ask any questions. And I also want to make this as interactive as possible, so I'll ask questions along the way. Okay, awesome. So message passing, we're all very familiar with this in the context of most likely graph neural networks, but machine learning uses distributed algorithms on a graph G comprising vertices and edges. And within this framework, each node Vi in our set of vertices does some local computation, which depends only on the information at the node Vi, its neighbors, and also incident edges Eij, so any edge connecting the node Vi to its neighbors within the set of edges. And we further know that information is sent through the edges to each vertex Vj as a message, Mij. So why do we care about message passing algorithms? They're very effective in practice. There are a lot of different places in which message passing shows up in machine learning, from graph neural networks and transformers to probabilistic graphical model inference and value iteration for Markov decision processes. And actually today, we'll go over all of these, but then also connect some of these algorithms together and show how they're well aligned with each other. These are also very easy to parallelize if we conceptualize them in the right way. So the plan is to cover better understood, more interpretable models and algorithms. So this includes PGMs, inference algorithms, MDPs, shared decision algorithms. And we're going to look at what components, what do the components of the models represent? What objective functions are the algorithms optimizing for, often implicitly? And then subsequently, we'll discuss more flexible, less interpretable methods, such as graph neural networks, attention networks, transformers, and connect them to probabilistic graphical models, MDPs, to help understand the inductive biases present in these less interpretable methods. Okay, so let's start off with PGMs. So in this case, we're going to focus on Markov random fields. We have n random variables, x1 to xn, and we have this joint probability distribution over all the random variables. And we kind of can look at this in a factorized form. So we can express this joint distribution as the product over a bunch of different potential functions that take as input a subset of these random variables, and then divide by a normalizing factor. And in particular, we might see that we have m non-negative compatibility or potential functions phi a to phi m, and xa, the argument of any potential function phi a, is going to be a subset of the instantiation of these n random variables. And then z, as I said before, is the partition function. It's a normalizing constant. So let's take a look at the diagram on the right. We see that we have 4 random variables, and then we have 3 factors a, b, c. And so then we can express this joint probability distribution as the edges represent the inputs to these different potential functions. So we see we have phi a looking at the incoming edges, we have x1 and x3, and so it takes us input x1, x3, and so on for phi b and phi c. And then we divide by this normalizing constant, which is going to be looking at the sum over all of these and making sure that we divide so that the joint probability distribution is a valid distribution that sums up to 1. Right, so we can rewrite the compatibility function when it's positive as in this way. We can write the joint distribution as we had before, 1 over z times this product of the compatibility functions. And then we can do e to the power of the negative energy, where the energy is defined as a sum of the logs of the potential functions. So before I keep on going, are there any questions so far? I think this is all stuff that we covered in the PGMs course that we did a couple of quarters ago now. Okay. So now let's take an example of how this might be used. Take error correcting codes Does anyone want to try to explain what the different factors here could represent within the error correcting codes problem? So just to make some of the notation more precise, error correcting codes basically mean that we receive some bits and we have this code word. So there's this kind of, there are these bits here that form maybe an image that we care about, but because of noise within our communication channels, we might have corrupted bits. But then we also have some parity bits, which impose some constraints so that we have a way of reverse engineering the bits so that they're uncorrupted. So the input variables here, yi, are the observed bits, but they might be corrupted versions of the xi random variables here. And we also have some factors. So in particular, could anyone try to guess what the significance of the factors are?
Can you explain that? Especially what's the notation of that like summation, special summation symbol here?
Yeah, so I don't, this is kind of like one, they're like the parity based error correcting methods. So we look at XOR of the bits, and we know that the uncorrupted versions of these xi need to satisfy some relationship. So we might know that we create this parity of bits so that x1 XOR x2 XOR x4 must be equal to 1. And this is one constraint that we use to reverse engineer the original image.
Okay, so it can be considered some sort of constraints that the domain experts giving, right?
Yes, yeah. So
Okay.
we're constructing the parity bits specifically to follow this, and it's proven that if all the constraints hold, then we know that this is the original code word.
Mm-hmm.
So given that information, do you have any guesses for what the factors here in this rectangle and also the factors A, B, C could mean?
So I can say that x1, x2, they should be the value for those pixels. But for ABC, I don't have this good intuition.
Right. So just to go over what this might mean. So for y1 to y4, these are the observed bits. They might be corrupted versions of the true bits that we care about. So again, here, this code word is what we care about, but there is going to be a lot of corruption in the communication channel. So the y's are going to be what we observe. The x's are going to be the actual values of the bits, like what they're supposed to be, assuming that there was no corruption. And these factors here represent the potential between the corrupted bit and the uncorrupted bit. So we kind of have this understanding of the probability of x1 given y1. That's kind of what this factor might represent. It's going to be proportional to this conditional probability. We want to know how likely is it that x1 equals some value given that y1 was the value that we observed. And then in addition here, for this ABC, these are representing the potential functions here are like with the hand engineered functions that represent the parity constraints. So we have a measure of the compatibility of the uncorrupted bits based on how well they satisfy this constraint that maybe x1 XOR x2 XOR x4 is equal to 1. Does anyone have any questions about how this was formulated? Is it clear? I just want to make sure that it's clear before I continue.
It's clear to me. I don't know how about others.
Okay. I will go to the next example, but please be more familiar for this. So we're going to look at maximum A posterior marginals and that it's objective to find a state X that maximizes the joint probability distribution. and it equivalently minimizes the energy. So remember, we had seen here that in order to find the instantiation of X that maximizes this joint probability distribution, we can minimize this energy as an equivalent objective. And we also care about the marginals, so probabilities for individual variables. So this notation here means that if for taking the joint probability distribution for some variable xi, some particular value of the variable xi, we want to marginalize over all the other random variables and all the values that these random variables could take on. So we're just summing out all the other random variables so that we can get the distribution just with respect to this one random variable. And we also have a partition function. So this is where we take the sum of this joint probability distribution over all the possible instantiations of the values that the random variables can take on, and then divide so that we can ensure that this joint probability distribution is indeed a valid distribution and sums up to 1. So let's take an example of semantic segmentation. So we look at a conditional random field. So this is the conditional distribution Px given I. So I is the image. And we know that it has this form where we're looking at e to the power of the negative energy of x, the random variables given I, divided by our partition function. So for semantic segmentation, there's a bunch of different energy functions that we could use for different tasks. But for semantic segmentation, we would like that if I is the image and X is the semantic class label, this energy function. Can anyone provide maybe the interpretation for why we might want this energy function for semantic segmentation? How would you what is the intuition behind this energy function? So just to be clear, semantic segmentation is kind of separating pieces of an image apart from each other. So let's take the biker here. We might want to say that the pixels here belong to the biker. And so the semantic label of these pixels is biker. And then the green here, all the pixels in green, the semantic label is the bike. So with that information, how might we interpret this energy function?
I think the first part is like the label is related to its pixel value. Second part is like the nearby pixels will share the same label.
Yes, exactly. That's perfect. So we have two pieces of information we need to take into account. Adjacent pixels have a high probability that have a higher potential function, representing that higher probability of belonging to the same semantic class label. And we also want to take into account the pixel information when making this decision. Okay, so with all that information, we're going to look at our first message passing algorithm, which is belief propagation. And so the notation here is a little bit confusing in my opinion, but I think we can kind of work through it. So let's first look at the messages for the random variables. So I guess just as a high level understanding of what we'll be looking at, we have the random variables on one side, and then we have the factors on the other side. And they're both going to be receiving messages and then sending messages to other variables. So all the n's represent the messages that a random variable is going to send to a factor, and the messages m are the messages that a factor is going to send to a random variable. So let's look at n sub ia. This is the message that variable I is going to send to factor a for a particular value of the random variable xi. So actually, let's take the example of x4. So for x4, we're going to look at all the values that x4 could take on. So all the values in its domain. Let's say that the first value we care about is 0. So we'll compute a message for x4 being equal to 0, and the messages that it might send to each of these factors b, c, and d that it's connected to. So the message that x4 is going to send to b is going to be the product of the messages that it receives from the other factors that it's connected to. So whatever message x4 sends to B is going to be equal to the message C sends to x4 times D sends to x4. Similarly, whatever message x4 sends to C is going to be the product of the message from B to x4 and D to x4. Now we're going to look at the messages that the factors send to the random variables. So for every value in the domain of any of these random variables, we'll take a sum over all possible instantiations of the inputs to a factor, holding the variable that we take as input xi constant, compute the potential function, and then do this product over all the messages that are coming in. So let's take, for example, let's take, for example, B. So the message that B might send to some variable x4 is going to be, let's take all possible instantiations of x1 and x2, because those are the variables that are not x4, hold x4's value constant, and then compute the potential function of x1, x2, and x4, and then multiply that by all the incoming messages from x1 and x2, but not x4. So are there any questions about this algorithm so far? Does anyone know the benefit of something like this as opposed to, I guess a first question I could ask is, if we want to compute the marginals, why don't we just do this? Why do we need the message passing algorithm?
Yeah, I think it's mainly for efficiency consideration because the message can be reused.
Yes, exactly. That's the right answer. So can anyone tell me how many different possible combinations I might need to instantiate here in order to compute the marginal? Right, so if we have n random variables and we're holding one of them constant, how many different instantiations of the other n-1 random variables do we need to consider, assuming that they're like binary random variables?
I think it should be 2 to the power of n-1.
Yes, exactly. So it's going to be 2 to the power of n-1, whereas here we see that this is actually a proof that you can look up. I'm not going to cover it here because there's a lot of other content to get to, but we can see that if we rearrange a lot of these factors when computing this marginal probability, we can move some of these summations in to these factors. And then these terms can be reused instead of having to compute them over and over again. Essentially, what we're doing here is leveraging that the factors only take as input a subset of the random variables and not all of them. So this is kind of like a efficient conceptualization based on message passing to compute this marginal probability without having to sum up over every single instantiation, but leveraging this information that each factor only takes in a subset of all the random variables. And to compute the marginal probabilities B, so this is our belief, it's going to be proportional finally to the messages from all the factors that a variable is connected to. So finally for x4, we'll just take the messages from B, C, and D, multiply them together, and we'll get the belief for x4. And if we instead this is called a sum priority algorithm, it computes marginals, but let's say we want to solve the map problem, we can just replace the sum with a max. So instead of having the sum here, we can just replace this with a max operation. And this works exactly in trees. So actually, like if we were to unravel this graph, we'd see that this is a tree, and the number of iterations, actually you'll see here that the number of iterations you need for this to converge to the right value is on the order of the depth of the tree. So we see that if you do this message computation in parallel, like the green and the blue in parallel at each iteration, then after on the order of D iterations, where D is the diameter of the tree, all messages and all marginals are correct. And it suffices to pass messages from leaves to the root and back. And so we might also see here like loopy belief propagation, given that we are only considering the case of trees. There's also the case where there might be some cycles. And what do we do in that case? So there is an algorithm, loopy belief propagation, which is kind of an approximation algorithm. And we don't really have a good understanding of when it converges, but we still apply the algorithm anyways, taking directly the one that works for trees and applying it to graphs, with more general graphs that could potentially contain cycles. So it's the exact same algorithm, and we're computing all these message updates in parallel. But belief propagation may fail when there are cycles. It may not even converge, and it often works well in practice, though, when it converges. So how can we exactly understand loopy belief propagation? This seems important because if we want to look at alignment with respect to something like graph neural network, which takes more as input more general graphs, we want to see if we can have a better understanding of loopy belief propagation. So we'll use some ideas from variational inference. I guess before I continue, are there any questions so far about what we've discussed? Okay. So variational principles. A variational principle solves a problem by viewing the solution as an extremum of a function or functional. So to understand or interpret an algorithm, we're going to ask what objective might the algorithm implicitly be optimizing for? So in standard variational inference, we're going to approximate what we call the Helmholtz energy. So the Helmholtz energy is equal to the negative log of this partition function. And it's going to be where z, again, is the sum over the exponent times the negative of this energy. And the probabilities are equal to, for individual instantiations of the set of random variables, e to the negative energy divided by the partition function. So we'll get to this derivation in a second, but for target belief P and arbitrary belief Q, the Helmholtz free energy is going to be equal to f of Q minus the KL divergence of Q with respect to P. And FQ here is what we call the variational free energy. And it has this form that's in the yellow box right here. And we're all familiar with the Kullback-Leibler divergence between Q and P. So how can we prove that this is indeed the case? So I guess if anyone, actually, I'll walk through it, but definitely in certain steps, I'll ask if anyone can explain how we got from one step to the next. So let's take this expression here for the joint probability. So if we take the log of this joint probability, we know that by our log properties, we get negative of the energy minus the log of z. And then furthermore, we see here that the Helmholtz energy, which is equal to the negative log of z from this definition that we've have up here, is going to be equal to q times x, q of x times the energy of x plus the sum of over all x of qx times log p of x. And let's see, we're trying to find out where we got to the next step from. Right, so we add this and we subtract this as well. I see. Okay, so we have this expression that results from considering the energy, the Helmholtz energy, and so we have qx ex plus we add this term qx log p of x, And then we also see here that we have this term from before, and then we subtract the summation term. And then combining these last two terms, we can actually generate, combining these two terms here, we can see that we get the KL divergence. I think I understood this proof before, but I'm kind of don't know where some of the stuff went. So we have these two terms from here, from the Helmholtz energy. Oh, I see. Okay, so I believe, okay, so this I guess we plug in log p of x here, and we can expand, and then we get that these two terms, got it, combined to the KL divergence. So the interesting thing about this formulation of the Helmholtz free energy is that we know that the KL divergence in particular is always going to be greater than or equal to 0, and is 0 exactly when Q is equal to P. So from there, we can find that the variational free energy is an upper bound for the Helmholtz energy. So minimizing the variational free energy of an arbitrary belief Q improves approximation, and it's exact when Q is equal to P. And minimizing f of Q, unfortunately, is intractable in general, but we can use approximate methods to find a tractable. So we can find a tractable Q and then use that kind of approximation to minimize this variational free energy. So one particular way to do this is using mean field. So mean field uses a factorized belief where we assume that we can write the belief of the joint for all the different joint distribution for all the random variables as a product of some beliefs over individual random variables. And the mean field is often solved by coordinate descent. So we can optimize one variable at a time, holding other variables constant. So this is just the same expression that we had from before, where what we're doing is taking we're taking e to the power of the negative sum over all the different negative sum over, yeah, okay, they're taking the negative sum over all the, so this is the mean field component. We're taking the negative sum over the product of the individual random variables times the energy, and then dividing by this partition. And so if we hold x constant and then kind of find the x that minimizes it while taking all the other possible instantiations of the other random variables, we'll find that this kind of coordinate descent converges to a local optimum. And this local optimum is a fixed point of updates for all variables. Okay, so there was a lot of information that was thrown out there, but does anyone have any questions about the last few slides? Are there any questions about any of these slides?
Would it be possible to go over the derivation one more time?
Okay, yeah. So the derivation keeps, like my understanding keeps on going in and out, but let's see if we can try to figure it out together. So we have this log of the joint distribution, which is going to be equal to, this part's fine. We also see that this is negative log of z, and this is coming from,
for this portion, I fear it's like, because log z's partition function has nothing to do with z, to do with x. So then we can just multiply that negative log z with this summation x qx, because that equals to 1.
Oh, I see.
And then we expand that negative log z as the summation of the two items.
I understand. Okay, so we add the energy to both sides of this and then multiply by by this arbitrary belief Q and then sum over all X. And it should give us this log C or negative log C. Okay, thank you, Professor Sun. That makes sense. Okay, yeah, so that makes a lot of sense. So we add the energy to both sides, and then multiply by this distribution Q, this joint distribution Q, and then sum over all values of X, and we get a value that's equal to a constant negative log C.
Right.
And then from here, we see that the first two terms are the same, and then the last two terms, we're adding one and then subtracting it, so that becomes 0, and these expressions are equivalent. And then here we combine the terms in yellow to get the KL divergence as the last term. And then the other two terms combine to make the variational free energy.
I see. Yeah. Okay. That the last two steps make sense. That I was confused about the equivalence of like the Helmholtz free energy. So now I understand. Well, thank you.
Okay, awesome. Does anyone have any other questions about any of the variational stuff here or terminology? Okay, great. Let's continue. So we can actually view this mean field optimization as some kind of message passing. So we have this expression for the energy that's the negative sum of the log of all our potentials. And if we look at how we've expressed these potentials above, we see that it's this right here, the sum over all instantiations of, the sum over all possible instantiations of X while holding Xj constant times this mean field approximation of the arbitrary belief Q times the energy function. So that's kind of what was here. And instead we're plugging in the energy function in terms of factors. And now we can actually just write the same thing twice, but one in terms of the factors that are neighbors of a random variable J and the factors that are not neighbors of a random variable J. And so we see that because these factors are not neighbors of random variable J, so Xj is not an input to any of these factors, this term itself is a constant because it does not depend on Xj. So it's constant in terms of this Xj as input to Q. And as a result, we only really need to compute, to compute Q Xj, we only need to compute this potential function for neighboring factors, which are within the, so neighboring factors, I guess, like the factors that are in the neighborhood of Xj. And you can kind of already see here that because we have this thing over the neighborhood, this is some kind of message passing algorithm. And in addition, all the computation only depends on the neighbors as well as the value of Xj itself. So just more formally, as a message passing algorithm on a factor graph, we do exactly what we did here, where we treat this this term here that starts with the sum over all instantiations except for Xj, all the way to the end here as the message. And then we kind of take this message and sum over for all the factors. And then we can kind of get this Qxj. So again, just to go back to how we derive this, everything from here all the way to the end is our message. We sum up over all the neighbors, and then we can compute Q as 1 over Z times e to the power of these aggregated messages. Are there any questions about this part? Okay. So now we're going to try to understand loopy belief propagation and the beta free energy. So for a tree structured factor graph, the variational free energy can be shown to be equivalent to this expression here. And this part I'm going to be a little bit hand wavy for the sake of time, in particular because you can actually look at the derivation in the appendix in the slides, which I sent over email, but we can see that it's equivalent to the sum of the variational average energy and variational entropy. Don't worry too much about this because we're going to continue and it's not brought up much later. But we can kind of make the same assumptions about an arbitrary graph that may have cycles. So the variational free energy is going to be approximate for an average while the variational free energy for the tree structured factor graph is this. For the Bethe approximation, we're going to use a very similar idea where we're going to look at the variational entropy summed with the variational average energy. But it's going to be in terms of what we call the Bethe free energy. And it has the exact same expression, but again, this is for graphs that may not be a tree. However, we're also going to impose some additional constraints during this optimization. So we want to make sure these are valid probability distributions and that the marginalization actually makes sense. And there's a result that showed that this loopy belief propagation gives the stationary points of the constrained Bethe free energy. So if we have these constraints, this Bethe free energy is expressed similar like it was to the tree structured factor graph as sum of variational average energy and variational entropy, then we get the stationary points through loopy belief propagation of the constrained Bethe free energy. And notably, there may be no distribution Q whose marginals agree with QXA. And so these are called pseudo marginals. And the Bethe entropy is an approximation of the variational entropy when the graph is not a tree. So in particular, this kind of is a way to understand cases in which a general graph may yield convergence for something like loopy belief propagation. But again, there's no guarantee that there exists some distribution Q whose marginals are going to agree with this. So like we may be able to ensure the first two constraints, but we might not be able to ensure the third constraint, in which case we call these pseudo marginals instead of actual marginals. So just a summary of these variational inference methods. The mean field minimizes the variational free energy. It assumes fully factorized Q for tractability. It can be extended to other tractable Q. It minimizes the upper bound of the Helmholtz free energy. It converges to a local optimum if coordinate descent is used, and it may not converge for parallel update. And the update equations, as we saw, can be computed as message passing on a graph. In contrast, loopy belief propagation can be viewed as minimizing the Bethe free energy, which is an approximation of variational free energy. And we saw that it may not be an upper bound for the Helmholtz energy. The resulting Q may not be consistent with the probability distribution, and it may not converge, but we can still use the message passing on a graph idea to kind of conceptualize this. We can also learn parameterized compatibility functions. So these potential functions can be based on some parameters theta. To do this, we can use maximum likelihood estimation. If some variables are not observed, we can also use the expectation maximization algorithm. And we can also use variational EM. So basically we can find an upper bound and then make this upper bound tractable and minimize this upper bound using the EM algorithm. And there's also other techniques that we can consider, like treating the parameters as latent variables and using variational Bayes. Okay, so are there any questions about the first part, PGMs? We're going to move on to Markov decision processes next. Okay, great. So for Markov decision processes, I think some people here might be a little bit more familiar with this in relation to reinforcement learning, and they definitely can chime in if I say something wrong, but just going to try to explain some of the terminology here first. So a Markov decision process, or MDP, is defined by a tuple of states, actions, transitions, a transition function, and rewards. And a state S is our current description of the world. The Markov assumption states that the past is irrelevant once we know the state, the current state in particular. So we'll kind of have this recurring example of navigating a robot, and the state is going to be the position of the robot. the actions for this robot example are going to be the set of available actions. So you can move north, south, east, or west. We also have a transition function. So the transition function takes as input your current state, an action, and then a next state S prime, and it outputs the probability of you transitioning to S prime given that S, given your current state S and some action A. So let's say that we have a robot here, like we do in this position 1, 1. Actually, that's not 1, 1, that's 1, 2. And if we have this robot in position 1, 2, and this is a totally deterministic robot, and we tell it to step towards the east, what is the resultant state going to be, and what is the transition function? So I guess ignore the probabilities here, but if it's a deterministic robot that's just taking a step towards the east, what is the resultant position and what is the transition function?
So the position will be just on the center cell. And for the transition function, because you mentioned it's deterministic at this moment.
Yes.
So then it's going to be the probability transition probability is going to be 1 to that specific cell.
Yes,
and,
great.
Okay.
Yeah, I just that's the answer I was looking for. Of course, I just wanted to kind of illustrate how even for deterministic problems, it's going to be a subset of this more general framework of the transition based on probabilities. So if we have the robot starting at this position 1, 2, and it steps over to the east and gets to position 2, 2, then the transition from state 1, 2, given with the action moving east to the position 1, 2 is going to be equal to 1. And actually the probabilities are going to be 1 for all different kinds of S and S prime, assuming that S and S prime are adjacent to each other. So as long as there's a valid action that can take you from S to S prime, then the probability of S prime given S comma A is going to be equal to 1. However, if they're not adjacent to each other, there's no valid action that can get you from S to S prime, it's going to be 0. But again, that's just a subset of a more general framework where we might have different probabilities given an action of going from this square to some of the other squares. Like the going east might just have a much higher probability than moving diagonally. We also reward function R, and this reward is received when an action A in state S results in transition to state S prime. So we have the reward function takes as input current state, the action, and the resultant state. And let's take this navigation example. So we're going to give the robot a really high reward if the resultant state is home. We want it to reach home. So let's say like this is S prime, then we're going to give it a reward of 100. If the robot is in a danger zone, so like where one of the crocodiles are, we're going to give it a reward of -100, and it's going to be -1 otherwise, because we don't want this robot to just move anywhere. We want it to take the shortest path back home. So the more steps that it's taking, the higher the penalty it's going to receive for taking a really loopy path back home. We want it to kind of take the shortest safe path back to the top right corner of this grid. So let's look at a graph representation of the transition function. So we see here that we have maybe some state S naught, and there's a couple of actions that we could take, A naught and A1. So we have these actions that correspond to a state S0. And if we choose to take A0, there's a half chance we might stay in state S0. There's also a half chance we might end up in state S2. Instead, if we take action A1, there's a 100% chance we'll end up in state S2. We also have this concept of policy pi, and this is a function from the state and time step to an action. So it's kind of a function that tells you if I'm in the current state at a current time, what action should I be taking? And we have this concept of a value function. So it's a measure of how good is a policy pi when started from a state S. So let's look at the value given a policy pi starting from state S0. It's going to be our expected reward. Like if we have, I guess the good way to explain this is, let's say we have, so this is a notion of a horizon t. So let's say we have a path between where the robot's starting and t steps. So the t steps could take us home, it could take us elsewhere. For each transition along this path of t steps, what is the expected reward of going from a state st at some time, using the action given by the policy that considers the current state as well as the time, and then going to the next state st+1. So if we kind of have the robot like take some random path that involves t steps, if we sum up the expected rewards across all the steps that it takes, that's going to give us the value of a given policy. And so then we can actually optimize this value with respect to the policy to find the best policy. We can also consider the case when the horizon is infinite. So there might be a reward, a discount. We might discount the rewards. There might be a discount factor that's put into the expectation. And so this essentially ensures that this expectation will converge. The summation will converge rather for a given value of a policy function. And of course, to make this converge, we need this gamma to be in between 0 and 1, exclusive of 1 and 0. Does anyone have any questions about value functions or policies? Anything that I'm missing for like the reinforcement learning experts in the room? Okay. So we're gonna, I guess as I alluded to before, if we can write this value function in terms of some policy pi, we want to find some optimal policy, and that optimal policy is going to, so I might have said minimize before, but we're going to maximize the value here. We want to increase the reward that we get along the way to the final state along this length t path, and choose that policy pi star as the policy that the robot should operate under in terms of navigation. So I think we talked a little bit before about having these crocodiles count as -100, the home count as 100 reward, and then any step that a robot takes is going to count as -1. So if we really want to find the best policy, we want to find the shortest path so that we incur -1 the fewest number of times, such that we also don't incur a reward of -100. So we want to be safe the entire time we take the shortest path. And then we also want to find the path that gets us back home and gives us that reward of a +100. And any policy that optimizes this value, I guess like the expectation of the rewards taken along this path with the given reward function, is going to be an optimal policy. So for solving MDPs, we can kind of write this as a dynamic programming algorithm. So let VST denote the optimal value at S when the horizon is T. And so we can write this we have a recursive relation here. When for VST, we're going to choose the action that increases our maximum expected reward, which is going to be the expectation of the reward if you're at a state S, taking an action and ending up in a state S prime, plus the value of starting at this next state S prime and having a t-1 steps left to reach the end of your path. So hopefully home, but just some length t path. We have t-1 steps left in our horizon. So we want to pick the action that maximizes this. And of course, like we have some initialization v S as a starting state. And if we expand this, we're going to maximize So we're expanding the expectation. We're going to maximize with respect to the action the probability of transitioning to S prime given some action and current state S times the reward corresponding to S, A, and S prime plus the value of starting at this new state S prime and having T minus 1 steps remaining. So does anyone have any questions about this recursive relation here? Okay. So we can actually look at this as message passing on a graph, and namely the transition graph that we had seen previously. So for a node at each state S initialized to this initial state, we're going to utilize A heads, one for each action A. So let's look at each action of each state S. So let's take S0 again as our example, and we're going to look at each action corresponding to the state. We have A0 and A1. We're going to do this in parallel. We're going to look at the probability of transitioning to S2 given A0 and S0 times the reward of taking this S0, A0, S2 decision plus the value of S2. And this is, of course, related to the value we're trying to maximize here. So we do this for all our actions, and then we sum up all the messages. And so that's this sum here. So we take the messages from A0 and A1, sum them up at S0, and oh, sorry, never mind. I should be a little bit more careful, actually. So the summation does not happen here. It happens at the actions. I'm going to repeat what I just said. We're going to look at each action of each state S. So we have S0, we have A0 and A1 corresponding to this S0. So we're going to look at 0.5 times the reward of this path here, plus the value S2, plus 0.5 times the reward of taking this path here. So from S0 back to S0, plus the value from S0. This is one message. From S0 back to S0 and S2 to S0. So we're summing up all these messages for possible next states. And then once we have the sums at these actions, we'll take a maximum of these sums at the actions to get the value corresponding to S0. Does anyone have any questions about this? I'm happy to explain it again if necessary. I mean, I think we can see here that this is very similar to like the GNN framework of message passing. So we're kind of doing this aggregation function here, and then we're doing the update function with the max. So each of these is a message. Each term in the summation is a message. We're summing up over all the terms and then updating using the max. Okay, so I'm not going to cover this in too much detail, but basically just very similar reward system as to before. We'll see the value here starts at 0, and then we're going to have a negative infinity value for all the other states. And we're going to have a deterministic transition function. And any kind of self loop back to itself is going to be 0, and any reward from transitioning for I to J is going to be negative W. So we want to penalize not taking the shortest path. And we can use, because it's deterministic, we can use the Bellman-Ford shortest path algorithm. And if we do this over some number of iterations, we can actually see that the values at each node are going to be the negative shortest path from that node to the goal reachable within k steps. So here we see the shortest path is 1. Here we see the shortest path from all these nodes is 2, and so on. So once we do this enough iterations, we cover the whole grid, update all the values, the value function for all these nodes in the grid. We'll get the shortest path and a good policy for the robot to navigate from this starting point to home without going into any of this dangerous territory. So for the infinite horizon discounted case, we are just gonna put the gamma here right next to the value function starting from the next state. And then we can just use the same value iteration algorithm with the methods changed to including this gamma factor. And we see that there's actually this Bellman's principle of optimality, where if we denote this as the Bellman update, so the value at time t of a given state, the value at time t plus 1 of a given state, we're trying to see when this value function converge using value iteration, then we can write it as the value function at t plus 1 equal to the Bellman operator times the value function at t. And what we care about is the fixed point of this operator. And the iteration algorithm is going to look like this, where effectively the difference between the value function at any 2 times is going to be equal to, it's going to be equal, not any 2 times rather, the two different possible value functions after one application of the Bellman operator is going to contract. So the difference between these two. So effectively, it's going to contract to a single point if we apply this enough times, the discount factor. Right, so the distance here converges exponentially to 0 for any initial value v naught. And once we apply this Bellman operator enough times and this gamma goes to the power of t, for t really large is going to be 0, we will see that it'll converge to some fixed point v, and it'll be a unique solution. So I guess this is not extremely relevant, but the value function is itself unique. However, the policy doesn't necessarily need to be unique. That's something to note. So we can optimize the value function, but have a bunch of different policies that could get us the same optimal value function. Does anyone have any questions about the MDP section? Anything that I can cover again? Okay. So I'm going to go through this a little bit faster because I think we're all very familiar with graph neural networks, but the message passing GNN formulation involves a graph, and we have our node features. We have as well as some edge features, and we want to output some label or value for graph classification or regression, or a label or value for each node. And so the way that this normally works is we have some D layers in your graph neural network. And so for each edge, we take as input, to construct the message, we take as input the center node I, we take as input the neighboring node J from the previous layer. We look at their features. We also take the IDs of these nodes possibly. So we might take VI, VJ, and then we also take the edge attribute and we compute a message M. And then at node I, we do this local computation where we update the value for node I at layer L, the feature for node I at layer L, using some kind of aggregation. So yeah, we're going to use some aggregation, yes, over all the different possible messages that are coming in. And at the very end, we can look at the raw representations, or we can do some kind of readout function that gives us a graph label or node labels. So there are some GNN properties. If the depth and width of a GNN are large enough, then the message functions and update functions are sufficiently powerful. And this is a result that comes from the local model in distributed algorithms. However, as we know, GNNs are parameterized, and so we just can't have infinitely deep and wide GNNs. And this means that they're not going to be sufficiently powerful for every single possible graph that exists. And when using GNNs, we're often interested in permutation invariance and equivariance. So in particular, invariance, I think as I think Fred talked about this when discussing Michael Bronstein's presentation at iClear. If we apply these permutation operators to the adjacency matrix and to the features, then we shouldn't have any change in the output of the function. This is invariance. And equivariance is when we apply these permutation operators, and then this permutes the output. So we actually can see that if the message function itself does not depend on the node IDs, so if we cross out the actual raw IDs for the nodes, then we get permutation invariance and equivariance for any permutation matrix P, but we will lose approximation power if the messages do not depend on the node IDs, because we will be unable to distinguish some graph structures, and this is related to the one-dimensional WL graph isomorphism test. And of course, GNNs are used for drug discovery and a bunch of other amazing applications. But now we'll kind of look at the algorithmic alignment of GNNs with some of the things that we've studied before. So we can actually see that the sample complexity for learning a graph neural network is smaller for tasks that the GNN is algorithmically aligned with. So this is our algorithm for a GNN that doesn't involve taking in node IDs. And it's very algorithmically aligned with the Bellman-Ford shortest path algorithm. So we see here that in the Bellman-Ford algorithm, if we had something like an MLP, if we had an MLP learning this kind of algorithm, it would require a very, very high sample complexity because it would have to learn this for loop that there's some local computation involved. So instead of the GNN, we have this for loop kind of built in to the way that this network operates, and in this way that it's very aligned with Bellman-Ford. Are there any questions about this alignment?
Can you elaborate more? I kind of lost about the purpose of this slide.
Right. So this is the pseudocode for a graph neural network, and this is the pseudocode for Bellman-Ford's shortest path algorithm. If we were to use the MLP to learn Bellman-Ford, it would require a very high sample complexity because we would need to learn that there's this local computation involved, this parallel local computation to do like the message passing and updating. In contrast, this idea of message passing is already built into a GNN. So we can have a lower sample complexity and better approximate something like Bellman-Ford shortest path algorithm with a GNN than an MLP could.
I think for this one, is that the paper that Zanil has presented in our previous reading group? I'm not sure whether Zanil is here or not.
It might be. I don't remember all the papers, but it's in use here.
Hello, hi. Okay. For the right-hand side, I think in the earlier slides, you described some like also iterative-based algorithm under the MDP part, right? You described the shortest path, which is message passing based idea.
Mm-hmm.
Yeah, and here you're saying that from graph neural network perspective, we can also try to use graph neural network to solve this shortest path problem, or we just wanted to put them in parallel?
A combination of the both. Like I guess the point being made in the slide is that this GNN cannot do shortest path because, of course, like there are some issues with not being able to take in node IDs and not being able to distinguish some structures. But if we try to approximate the shortest path, we need much fewer samples to approximate shortest path than MLP would, because it doesn't have the same message passing framework built in.
Okay, and then when we talk about sample complexity. So do you treat like each graph as a sample here?
Yes, I believe so. I guess, let's see. That's a very good question. I suppose it depends on how you define the task. It's not entirely clear from the slides themselves, but you could have multiple instances. You could have multiple instances across multiple graphs. So yeah, you could see you could probably get multiple training instances from just every pair of nodes within a single graph, but then you probably want to try across a whole distribution of graphs if you want to make the approximation more generalizable.
Yeah, I believe if we really want to understand the alignment, I think when they say alignment, they just wanted to try to put the two algorithms side by side, right? And then try to understand the limitation of graph neural network compared to other algorithms. So I really think if we wish to fully understand what they're saying here, we need to go to that paper.
Yes. I think it's a message.
Oh, Derek
From
says,
Derek.
okay, Derek, okay, can you speak up?
Oh yeah, sure. I think I presented the follow-up one to this one previously, and I think the idea in this one is if you're using the same kind of like knowledge as the true algorithm in your GNN, then the GNN is better able to learn the true algorithm. So here, you can treat each of the features as this DLV or DLU. And if your GNN's aggregation is like the min function, then this MLP part can learn the DL minus 1U plus WUV, since you can create a linear combination that gives you this value. In that case, the GNN can learn the same algorithm as the Bellman-Ford. But if you use like different kind of aggregations or different like MLP, then it's more difficult. For instance, if you're using like sum or like max aggregation, then it's a lot harder to approximate the same Bellman-Ford dynamic programming function. Is that clear?
Okay, so can I rephrase here? So for, I think in that paper, they try to discuss the kind of capability of GNN to see whether it can recover some existing graph algorithms, including the shortest path one, right?
Yeah.
Okay, and then for this slide says that if the aggregation function is MLP, then it will have the capability to recover shortest path. Otherwise, for example, if we just use simple aggregation like average summation, then we are not able to do that.
Mm-hmm. Yeah.
Okay, then can you explain a little bit about the low sample complexity and high sample complexity?
Oh, so my guess of what it's talking about is if the algorithms are aligned, like if you have good choice of aggregation and MLP, then it's very easy to learn kind of the true function. So it takes not as many samples to reach this like optimum that's similar to Bellman-Ford. But if you have like aggregation and MLP that's like not aligned with the algorithm, then it's kind of very hard, or in some cases like not possible to learn the same function as like the DP algorithm. So in that case, it would take a lot more samples to learn like a local minimum, because the local minimum that you learn is kind of different than the true like algorithm from dynamic programming.
Mm-hmm. I see. So it's not about the sample complexity for the shortest path algorithm, because it's not even a learning algorithm, right?
I believe they might have had some experiment where it's like comparing shortest path algorithm, like shortest path algorithm is like the ground truth, and you're trying to approximate the shortest path algorithm with a graph neural network.
Okay, so some of them, for example, if with MLP, then the sample complexity is low, but if it's not aligned, then we actually need much more samples.
Yes. Yeah.
Okay, great. Yeah, thank you. This is very helpful. Thank you, Derek.
Okay, so we'll now look at the alignment of a GNN and value iteration. So kind of looking at this sequence of two for loops, again with the graph neural network pseudocode and the value iteration pseudocode side by side, we see that a GNN can be well aligned with value iteration. So I guess one comment to be made about this is that if we have like robot navigation using a map, then the transition probabilities and reward functions may also need to be learned instead of being provided. So the message passing structure suggests that we kind of like represent the transition and reward separately, and use as input to the same function at all states. So we're kind of learning this R and these probabilities independently of each other. And then this kind of serves as an input to all kinds of updates at every single state. So the GNN being well aligned with value iteration may work well here because the value iteration itself has a stronger inductive because it's encoding these value iteration equations directly. So this is, again, just very similar to what Derek had said earlier. Basically, because we know like algorithmically and provably that these kinds of update functions and aggregation functions are the ones that work best because we're encoding this information directly, then there's going to be a much stronger inductive bias for value iteration. But the GNN could be more flexible, especially if like there are some assumptions that we make that are not accurate that a GNN could discover, particularly for like a specific kind of MDP. We can also look at the alignment of a GNN and graphical model algorithms. And the GNN and a graphical model algorithm are well aligned when the potential functions are pairwise. So the potential functions only take as input two nodes, or in this case, random variables, xi, xj. And what this implies here is, let's look at our mean field algorithm from earlier. We see that this mean field approximation, the product, because we're looking at all variables in the neighborhood of I that are not equal to j, we can actually just see that the mean field, the message here is only a function of qxi. So it only depends on qxi because we're not considering j. And we can send, therefore we can send messages directly from one variable to another variable without combining the messages at factor nodes. So again, because we don't really need, we're looking at these potential functions that only take as input two random variables, and this approximation only consists of only consists of qxi. We don't actually need, we can get rid of the factors and just pass messages directly between different random variables. And that's how the GNN is well aligned with the graphical model algorithms that we looked at previously. So we might ask then, how about higher order potentials? So again, for the sake of time, I don't think I'm going to cover this in too much detail, but basically like the high level idea is we can rewrite this potential function that takes in as input more than two random variables as a tensor decomposition, and then look at sums over all these different potentials. And if you definitely take a look at the slides here if you're interested in learning a little bit more about this. It's just that with this low rank tensor decomposition, we can rewrite this message passing with potentials that are take as input more than two random variables in a very compact way. And with this, they showed actually that if you apply this, it's very similar to, if you apply loopy belief propagation using this low rank tensor decomposition, It optimizes the Bethe free energy, as we saw previously, if it converges. And we can further neuralize loopy belief propagation. So I guess they have this high level idea of having some analysis where we start with the network representing the algorithm to capture like this inductive bias of message passing, and then add some more computational elements to enhance the expressivity and approximation capability. So again, like I'm not going to go into detail about the factor graph here, but if you want to neuralize this, we might first do this message passing and like create the messages as we would for the factor graph, usually with this low rank tensor decomposition, apply an MLP, and this kind of enhances the expressivity, and then we can use all kinds of aggregation functions to make to increase the approximation capability of something like a factor graph neural network. So the very last thing I'm going to cover is related to attention networks. So we're going to look at distributed representations of graphs. Suppose we have an adjacency matrix that can be factorized as a product of U and V transpose. So then U I transpose Vj is going to give you the ijth entry in our adjacency matrix. So if we actually use this matrix factorization, we can show that transformer type attention network is well aligned with value iteration for an MDP. So in the attention network, we have a set of nodes, each of which has an embedding as input, and the same operations are applied to each node in a layer. So let's just quickly recap how multi-head attention works. Let the embedding at a node I be xi, and of course we might have like k attention heads. We embed the representations of the input nodes using a query weights WQ. We also embed the input nodes to get some keys using WK, and we also can get these value vectors as well. And then we compute this attention between two nodes I and j, between the query for I and the key for j, with all other nodes j. And then we can compute the probability vectors in across the rows of this attention matrix by computing a softmax on the row. So then once we have these probabilities and multiply them by the values, we'll concatenate all the outputs across the k heads and then project it into a vector, same length, and then apply a feed forward neural network, which will then go into the next layer. And I know that usually attention networks may have a layer norm operator or something, but we'll be ignoring that for the case of looking at the alignment. So let's look at exactly how an attention network is aligned with value iteration. So we're going to carefully construct an input xi. So we're going to use matrix factorization to get a distributed representation of our transition matrix. So in particular, we're going to assume that there exist two matrices U and V such that UV transpose is going to be equal to L. And this L is going to be the log probability of transitioning to S prime, given that your current state is S and you take an action A. So this is just, we just are representing the transition matrix as the log probabilities of transitioning. And then these log probabilities we assume can be factorized into U and V transpose. And this is how we're kind of fitting the transition matrix into the framework of computing attention within an attention network. So to construct the input for a node I, we're going to stack up k+1 copies of the initial value vi. And then we're going to look at we're going to store the embeddings of the transition matrices for each state, for each action, for each state I here. And then we're also going to put the rewards for each action for each state I here. So there's going to be, just want to confirm. Right, so there's going to be, yeah, so just to recap, there's going to be the k+1 copies of the initial value here. There's going to be the rows of U and V being stored in the next few entries, and there's going to be the rewards being stored at the very top. And these rewards are going to be the expected rewards for a given action A and a state S. So we have K actions, and for each state I, we're going to look at the expected reward of RS, and then like of taking the action A from between 1 and K from a state I. Okay, so now to put this all into the attention network framework, we can see that as we constructed this very carefully. So if we want to compute the actual transition probabilities, we just take the dot product of the appropriate U and V, and then we exponentiate it because we had log probabilities for the transitions. And then we appropriately select out the parts of the input matrix. So using this identity matrix as the weights for our query, we're able to select out the values, the raw values for we're able to select out the raw values. Where are we selecting these values out? Oh, okay, so we're selecting the appropriate VKI to U1I here. For WK, we're selecting out the V's, and we're going to set the weight value to extract out the value components from the bottom part of this vector. So once we select out all these log probabilities, and then we multiply all of them together and exponentiate to get the transition probabilities, we're going to multiply these transition probabilities by the bottom part of this vector to then get the output for a single head. And then once we get the output for a single head, we can concatenate all these outputs together and add them to the first bottom k components of the input vector. And subsequently, we can use the universal approximation ability of a feed-forward neural network to do the rest of this computation. So we already have this expected reward, and we have already multiplied the value by the transition probability. So the exact computation here, you can take a look at afterwards, but effectively, because we just need to do this update and then we need to take a max operation, this feed-forward neural network can provide us with this ability, and then we just update our representation for each node and pass it on to the next transformer layer. And if we assume that this attention network is recurrent, so that all the weights in each layer are the same, if we do this iteration multiple times, we can get some kind of convergence of this value function. So we have these methods: backpropagation, recurrent backpropagation. All the methods discussed are message passing on a graph, and putting layers together with these feed-forward neural networks, or the MLPs used to create new features for the next layer in a GNN. We can get a deep network, and we can use gradient descent, assuming all the network elements are differentiable with backpropagation. And like I said before, if all the different layers have the same parameters, we have a recurrent neural network, and recurrent backpropagation is a lot more efficient. We can use constant memory usage in this case. So a quick summary of everything that was discussed. So there were some classic message passing algorithms that we looked at through variational principles, including loopy belief propagation, mean field, and value iteration. And we also looked at what kind of optimization problems they were solving. And then we're also able to relate GNNs to things like Bellman forward shortest path and attention networks to Markov decision processes and value iteration. And the kind of questions we asked were in the analysis, how can we align algorithms? Can we see how we can simulate any of those algorithms using a small network? And how can we neuralize algorithms? And can we enhance those algorithms into more powerful neural versions using parameters that can enhance the expressivity and approximation capabilities of the more classic message passing algorithms? Yeah, so yeah, the ending was definitely a bit rushed, but thank you so much.
Thank you, Arjun. I think it's a very clear presentation, and thanks for start this tutorial, which I guess it just happened about 1 month ago, right? Like in Europe. Yeah, I think it provides a very unique aspect, try to connect this traditional old approach, which is message passing, and into the more modern neural network, especially graph neural network. Yeah, very interesting topic. Thank you.
Yeah, I guess one thing that I know we're over time, but one thing that I wish the presentation had covered that I think would be really interesting for everyone to look at more too is this idea of logical expressivity of something like a GNN, and then using these alignment properties to study like what kind of logical queries can something like an attention network or like a belief propagation method, solve. So I think like there was a paper recently about how logical queries that are like a first order countable logic that involve two variables can be solved by GNNs, but how does that change with transformers and belief propagation? But yeah, it's a very interesting tutorial. And if you wanted to see the original video, it's also going to be made public soon, and I highly recommend that as well.
Yeah, for the logical expressivity, can you present next time? I think we discussed that briefly last quarter or so, right?
Yes. Yeah, I can, in a future reading group, I can definitely present this paper on logical expressivity. It's very interesting.
Okay, great. Thank you.
Bye, everyone.